So, good afternoon, everyone, and to Professor Said and Manas. I guess it will be good morning.
Morning.
Welcome to the tutorial of Explainable AI using knowledge graphs. This is the last event of the False Common 2021 session. Just before we start, let me give a small introductions to these speakers. Professor Amit Sheth, he is from Artificial Intelligence Institute, University of South Carolina. He's an educator, researcher, and entrepreneur. He's the founding director of the university-wide Artificial Intelligence Institute at the University of South Carolina, and previously he was the LexisNexis Ohio Eminent Scholar and the executive director of Ohio Center of Excellence in Knowledge-enabled Computing. He is a fellow of IEEE, AAAI, and AAAS. He has organized 75 plus international events and 65 plus keynotes, and he has also given many well attended tutorials and is among the well cited computer science scientists. He has founded 3 companies by licensing his university research outcomes, including the first semantic web company in 1999 that pioneered the technology similar to what is found today in Google Semantic Research and Knowledge Graph. Several commercial products and deployed systems have resulted from his research. So, welcome, Professor Seth. Our second tutorial speaker is Manas Gaur. He is currently a PhD student in the Artificial Intelligence Institute at the University of South Carolina. He has been a data scientist and the AI for Social Good Fellow with the University of Chicago and data miner. He his interdisciplinary research funded by NIH and NSF operationalizes the use of knowledge graphs, natural language understanding, and machine learning to solve social good problems in the domain of mental health, cyber social harms, and crisis response. His work has appeared in the premier AI and data science conferences like CIKM, WWW, AAAI, CSCW, and also in journals like PLOS ONE, Springer Nature, IEEE Internet Computing, and healthcare specific meetings such as NIMH, MHSR, AMIA. Welcome, Manas. Our third speaker is Keur. Keur Faldu is currently working as a chief data scientist at Embibe. He has founded and built the data science lab there, which is primarily responsible for building AI platforms for learning outcomes using intelligent content authoring and intelligent intervention leveraging educational knowledge base and the big data lake. He has more than 14 years of industry experience in data science, machine learning, deep learning, and natural language processing. He worked at startups like Vivio Inc. and Runa and also was part of the founding team for data science at McKinsey Digital Labs at McKinsey. He holds post-graduation in computer science from the Indian Institute of Science, Bangalore.
Okay.
Ankit is our fourth tutorial speaker. So welcome, Keur.
Thanks.
And Ankit Desai is currently working as an associate principal data scientist at Data Science Lab at Mumbai. He is involved in a process of architecting the knowledge graph, and he has overall 11 plus years of experience. Apart from working at Imbibe, he has published multiple research papers in the international conferences and journals. His research interests include educational data mining, graph mining, massive data sets, cost sensitive data mining, architecting the data science, and projects from scratch to production level interest him the most. Moreover, he has served as a review committee member for the conferences of ACM and IEEE. So, welcome, Dr. Ankit, I guess. And we are all looking
Thanks.
forward to your tutorial on explainable artificial intelligence. And as the title sounds, it is very relevant to the current research and also real implications for artificial intelligence in our everyday life. So, with this, I would like to hand it over to the speakers. Please.
Hi. Okay, so I'm going to get started. I'm Amit. We have all been introduced, so I will proceed. Next slide, Manas. Um, we're going to start with a quick overview of deep learning, which is in this decade become the most exciting, most important technology, certainly in AI, but broadly in much of the technology sphere. And um, while the concept and technology related to knowledge graph is not new, the word ontology, knowledge graph, taxonomy have been used for a very long time. Last 5 years or so, um, and especially after Google showed the huge value of knowledge graph in semantic search. I had done, a company that was doing similar thing earlier. Um, the last 5 years, good knowledge graph has really taken gotten a lot of attention. In fact, my keynote last year at CORSCOMAD was on knowledge graph. With the success of AI, um, but the deep learning being a black box, meaning it's hard to explain how deep learning algorithm came to a particular conclusion. Um, Explainability and interpretability have become extremely important, and so we want to essentially explore how the use of knowledge graph help us obtain a better explainability and interpretability for the statistical AI techniques in deep learning, and then we'll look at a couple of use cases. All right, so let's look at the black box feature of the deep learning. We are in what is called as the second generation or second take of AI. The AI phase one in 1980s, where AI was also very popular, um, was more along the line of what we call today symbolic AI. You had rule-based learning, you had description knowledge bases, and reasoning and such things. In this second phase that happened in this century, the knowledge, the importance of data took the center stage. And after that, in the first decade, there was a lot of progress in machine learning, so-called supervised machine learning. And then in this particular decade, in the second decade of this century, the deep learning, the learning directly from AI, from data, um, with lot many parameters and lot more computational power has come to the fore, to the in front, and it has shown some amazing outcomes, but it has taken a lot of computation, and it is hard to explain. So it has come at the power of uh, capturing a lot of statistics from the data, and what is very often need for a lot of labeling, a lot of annotation, and from that, a lot of so-called parameters have been obtained in how the data is interconnected to each other and what they explain. Now, with the success of deep learning, and you can see the plot on the right hand side. On the x-axis, you see the computational power usage that grows. On the right, side in y-axis, you see the parameters, and the left hand side, you see the y-axis validation loss. As you use more computation power, you have continued to improve the quality of results and made the model more and more complex. But there are a lot of challenges still remain that remain unsolved. For example, is there a bias, or uh, how as you already said, how the system came to a particular conclusion, and there happens to be um, many applications where it is not possible, where the users would not accept the outcome, or conclusion, or the guidance or prediction um, given by this deep learning algorithm, unless you are able to explain. So um, so it is really important to kind of open up the black box and somehow get in there and say how you came to that particular conclusion. There are a lot of challenges also that are listed on the left hand side: limited label data set, and it requires that the experts are really much in agreement with the amount of information you can convey to a deep learning algorithm through the labeling is very limited at some point. So for some problems where you have to classify in 2 classes or 3 classes, so if you have enough data, the results are fantastic. But there are many situations where um, the situation is a lot more nuanced. The experts are not that much in agreement with. In many of those cases, the deep learning algorithms struggle. Next. So um, semantics, which is about meaning, associating meaning with data, it has played very important role in many situations. Um, Today, while the first generation of machine learning based Google search did not understand what the words mean, today, to some extent, Google semantic search after 2013, the search engine actually understands what some of the terms mean. When you do a search term, if you use, let's say, the entity, uh, if it can match that entity with the entity in the knowledge graph, then there is an meaning associated with the word, and it is able to exploit. For example, a professor works at a university. That knowledge is something that it can exploit, and that comes from symbolic representation in the knowledge graph that it has, and that is what is leads to semantic search. That analogy also appears for the knowledge graph. Sorry, for the deep learning algorithm. Next. So there is a simple case. How there's a how many alcoholics are relapsing under lockdown? So question is, does a person have addiction? The response is yes, and answer is yes. What is next? But let us look at this other case where the context and the data presented is what you see there, and there is a lot more here. It's not that simplistic piece of information. And language is very complex. Language is can be very involved. So you have concept of depression. Then it says manic episodes aren't characteristics of depression, something that is a negation. And when you give such a text and ask the question, does the person suffer from depression? The model, particular model, that sequence to sequence model may would answer yes, but the real answer is no. So the reason is that manic episode is a characteristic of anxiety, not depression, right? So the mental health concepts of anxiety and depression are different, and here in the text you talk about both of them. Thus, it is not enough that your system exploits syntax. There needs to be a semantic for understanding, meaning you have to understand the meaning of depression, understand the meaning of anxiety, associated properties, and then you can answer this question better. The other example is that of reasoning. So here you have this is an educational scenario, and then the question is, uh, um, uh, you know, does for what causes forest fire? And you have some options. The answer is static electricity. and that is because you are able to uh, reason that static electricity can cause sparks, sparks can start a forest fire, and hence, right? So there is a chain of reasoning here, and such a thing, is normal for in symbolic AI, but not so easily done in the statistical AI. So that is another case where our deep learning algorithms don't do well. Next. So the main takeaway, the main aspect of this tutorial is that by adding knowledge to data intensive learning for uh, 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 we can have better outcome both for performance but also for interpretability and explainability. So there are a number of challenges. One of the huge success story in the recent years that demonstrate the power of AI is AlphaGo. This is a system that has huge amount of steps. So the space, search space is vast, right? And hence brute force computation is extremely hard to do. Now, in the AlphaGo, in addition to using very powerful algorithm, very powerful computation, it still would not have done great unless they used some core knowledge about the game. So, what constitute a good step that were captured in the form of rules, and then using Monte Carlo tree, you can say why you can explore the path taken to say why you chose that particular path to take your next step in the game. So this was a great example in particular for improving the performance of the deep learning algorithm by using some knowledge. We call it functional knowledge, right? Now there still remains a lot of challenge. It so happens that in the games like AlphaGo, the game does not change. But there are many things in the world that we do, including science, there our knowledge continuously evolve. In the example, when we talk about COVID, we of course knew very little about SARS-CoV virus and everything about its genome and everything about its function and phenotypes, and that we learned in less than a year. We have a lot more knowledge about this domain. So um, we need to evolve the techniques where we can continue to evolve up-to-date knowledge, right? So that is an interesting thing that we need to keep in mind. Next. Now, here's another example of what is considered to be a huge progress in, again, huge demonstration of AI's power. And there's recently, there was a solution from Google, DeepMind, I believe. So, about constructing the protein structures. So proteins start with amino acid and they fold. There are certain constraints, biological, constraints related to the folding process. Now, here also there is a the system was able to really gain, get that solution to a relatively complex problem, and complex problem both in terms of functional aspects, but also in terms of computational aspects, where there was some knowledge about what is a valid folding in the protein structure and what is not, that allowed the system to whittle down to navigate through the search space to get the valid protein structure, right? So with a lot of data coming from protein data bank and applying certain rules in addition to using very powerful algorithm that allows you to explore all the possible structures, you are able to come up with this solution. But even after that, the algorithm only gives you valid protein structures. There are many questions to be answered, such as for a given purpose, which structure would be the best, and what would be the appropriate functional properties of the structure. That would require use of infusing additional knowledge. Next. All right. So we look at some of the challenges. One of the challenge is to learning the long tail. In answering questions such as sodium azide is used in airbag to rapidly produce gas to inflate the bag, and then you want to be able to identify what how do you what is involved in this particular process of inflating airbag from the constituents, right? So in that case, you can see the process that is shown on the right hand side in the bottom. And as if you analyze this, number of things that become clear, that there is a involved, you need to really have some understanding of the domain, or that there is a domain specific knowledge, that there is a multi-hop reasoning that is happening. So you can't jump easily from the first step to the last step. And doing this kind of thing would mean that you really are that coming to the conclusion like this using a deep learning algorithm becomes either extremely hard or impossible. There are a number of these components are involved, and they are not the things that you simply can make the algorithm learn by giving lots of data and say go and learn on your own. There needs to be some direction as to what are the things you're looking for, and there needs to be also this procedural knowledge, or multiple steps of things to be done, as opposed to the results that come out from the output layer of a deep learning algorithm, right? Next. So if you, on the left hand side, you see the knowledge, the component of the knowledge graph. If you were to search for Barack Obama on Google, you'll see the information box that shows up. And in this particular case, the knowledge that Barack Obama is the 44th president is given very explicitly in the text, in the first sentence of this itself, right? And the information is there to be exploited in a much more clear way. But if you try to explain, so that when you combine that with deep learning, it is very easy to answer. But if you try to just use GPT-3, one of the latest of the deep learning algorithm used for NLP in particular, and it has so-called complexity algorithm is measured in terms of these parameters, number of parameters. It will say, I think it's Barack Obama with more probability than some other names. But when you ask why, that would be, it will know. There's hardly any way for the algorithm to explain exactly where. It could actually show you many places in the corpus where Barack Obama and 44th president comes in, but it would not be able to more conclusively say that I am relying on this reliable data to tell you this one. This is based on Wikipedia, that is a collective intelligence that many people edit, and that knowledge is supposed to be high quality. So here are some other examples of failure of Bert and Roberta. These are well-known uh, deep learning algorithms and approaches where you don't do too well, and there are quite number of reasons. On the modifier here, you see there's a task of sentiment analysis or duplicate detection, fairly basic task. Then there are modifiers. So you have short sentences with neutral adjective and nouns. And with these kind of examples, the systems have very, very high failure rate, right? You can see the duplicate detection where the order is irrelevant for comparison. The last item, are tigers heavier than insect? The knowledge is not there explicitly in the text, and then they totally fumble, right? So this also goes to show that there are. It so happens that for some problems, the machine learning and deep learning algorithms fit like a glove and really answer them very, give you what you need very well. There happens to be other problems where, in spite of them having amazing power, they fail on the on relatively simple looking tasks. So this again shows why um, statistical AI is not sufficient for a number of problems. Next. So here we show you an example on the this example is about how people's behavior affects the spread of COVID-19. And in this particular case, we are using a graph convolutional neural network, and we have concepts like shelter in place, and that causes anxiety, or shelter in place prevents anxiety. What would happen is that a purely statistical approach would not be able to make the distinction between these two concepts and when one is right or one is wrong. You see on the left hand side, bottom left, there is a knowledge graph, and there is a knowledge saying shelter in place causes panic reaction, uncertainty, fear, anxiety. When such a knowledge is incorporated into the system, now you can answer the question, if these two concepts, similar in place causes anxiety versus shelter in place causes anxiety versus shelter in place prevents anxiety, answer is no. So this is another example where combining knowledge or symbolic knowledge with statistical learning, helps to solve the problem that otherwise cannot be. Next. So in this example, you are using deep clustering techniques and neural parsing on a large corpus of ready data, and the system comes up with all the clusters. But it does not tell you exactly what that cluster stands for and how the clusters if are potentially even related, right? So we have a knowledge which provides the context. In this case, you see the anxiety, agitation, panicky, all those concepts being organized. That gives you a lot more specific understanding of what the data represents. If you just use the statistical techniques, you're getting some clusters, but then human, it does not give you enough insights into what that data has. With the use of context provided by knowledge, you are able to understand a lot more from the statistical analysis of the data. You are able to see that circadian rhythm disorder is very closely related to sleep disorder. And if the knowledge base says they are the same, then you solve the problem in that the data, underlying data, are also truly mirrors that knowledge. In other cases, you can explore related knowledges to anxiety from that. So labeling the cluster itself becomes possible with the use of knowledge. And in this particular example, you are able to, for example, take this processing, and you're applying, you can see here on, just under this A, B, and C. Under B, you see a variety of knowledge. ICD-10 is medical coding system. COVID-19 lexicon, it says what it means. SNOMED CT is procedures and other medical concepts that are organized. So these are all knowledge that are added to the this pipeline. And when this is done, you can potentially study that when people are not practicing social distance at will, these are all the concepts that come out. While when people are practicing social distance at will, these are all the concepts that come about. And so this, if you look at carefully, it can give you important cues that help you understand the human behavior that drives the outcomes associated with COVID-19. Right. So this kind of example become possible. The other example, other very important class of things that that will be impossible to explain using deep learning by itself is a whole variety of biases. And you have corpus. You are looking for image search of CEO. And 95% of the CEOs have been men, and that will kind of have that bias that the data has come out in the results. In many of the facial databases, there are very few people with color, and in that case, the system both fails to do the analysis, and that bias remains. So you would come to a conclusion that is unfortunate, socially not acceptable, and perhaps erroneous. So, and for the lack of time, I'm not going to go discuss all of this in detail. Next. So this is a very interesting example. Here we were studying the problem that we were studying was radicalization of social media. There are number of known cases where jihadis, the extremists from Middle East, actually convinced Western youth to join the jihad, travel to Middle East, or engage in violence. And studying this kind of stuff from short text and Twitter is extremely hard. What made it possible is the use of empirical model. We worked with a political scientist, and he had an empirical model where he said to study radicalization, you need to understand religion, ideology, and violence. These concepts separately. And we were able to, on the top right, you see, we are able to use the concepts of religion. In our case, it was based on Hadith and Quran. Concept of ideology, especially in extremism, and then we are able to distinguish that concept like jihad can be used in very different way. In the religious text, jihad is something pure and positive, while in the use of extremists, jihad is quite negative. And so on the bottom left, you see that there are two different contexts. One is the extremist context, and you can see the associated terms, and the one below that is the non-extremist context, as we use properly in the religion, and then you can see very different concepts are associated with that. So use of the knowledge here allowed us to look at this concept jihad from two different perspectives as the problem demands. Without this, well, jihad is one word, and you'll find out all the concepts related to that which deep learning algorithm can tell you. There are a lot more other things that you can do. On the image on the right hand side in the bottom, you can see that we have ability to associate variety of concepts and actually have exploit the relationships between the concepts also. That is the kind of power. The explicit power of representation relationships is something that is going to be missing in statistical AI, because you have terms and you find the statistics about how they are related in corpus, how often they come together, what is the number of average number of distance between the two concepts, all those kind of stuff you can compute using deep learning, right? But to understand that employee owns stock in a company and employee works for a company, very different relationship. To understand that there are these two things is very hard. Now the deep machine learning algorithm can actually recognize that there is probably two different relationships, but knowing what relationship it is again extremely hard for them to do. How do you label them, right? So these are the kind of challenges that infusion of knowledge and knowledge graphs can help you solve. So in this particular case, in the left hand side, you see a scene knowledge graph, and if you use a clustering, you'll find that cluster you see in the middle. But what happens is that because of the use of the knowledge graph, it was possible for us to really identify the events and also objects. So in the autonomous vehicle, the concept of scene similarity detection is one of the fundamental challenge or problem. Use of knowledge here was critical in developing a solution where the scenes could be much more analyzed to compute the similarity between them, right? And that became now if you apply a rule that a scene that has a lot of school bus means you have to drive slowly and be extra careful because there can be kids in that region, becomes a lot more possible. And without having the knowledge, the reason why the sensory data indicative of the scene that the scenes are similar to other scenes becomes extremely hard and probably impossible, right? So this is another very good example of what knowledge, in this case particularly, there are many ways that, Manas will talk to, explain to you different ways the knowledge infused. This is an example of shallow infusion. He will describe other types of infusion later on. Okay, so Manas, aren't you going to take here? I didn't see the separation between us.
Okay. Yes. So this is the last. Hello.
Hi. Yeah. Sorry to interrupt. Actually, we had a question in the question answer box, and
Okay.
actually, so Keur has already answered it, but I believe the question answers cannot be seen anyone other than the panelist and the host. So, in the interest of everyone, I am just reading out the question, and if Keur can like just iterate the same answer or anyone else. So Vinita asked, can the use of domain knowledge help in reducing the need for amount of data for DL models? If yes,
Yes.
Absolutely.
could you any with any examples? Yes,
Yeah,
please.
we'll show you the the example, but absolutely that is the case. Imagine that so many people have worked to create Wikipedia, and from that we can create DBpedia, which is model, which is a knowledge graph, and that is uh, at least as equivalent as giving the labels. It has millions of facts, and indeed that can be used as uh, uh, replacement for label. Not only that, depending upon the deep learning model used, there's more in DBpedia, including the relationships, the info box. There's more structure. So compared to the typical labeling, which is much more flat in terms of taxonomy, you can actually have more knowledge and more type of knowledge infused that you can't do it with just labeling. So yes, the simple answer is yes, but it's even more than just replacing or complementing or enhancing the traditional labeling. That the type of knowledge you can explain. First of all, Wikipedia means there is a level of agreement among the editors, and the second, the knowledge represented is richer than typical labeling. Hence, you can also exploit that knowledge. All right. So just to summarize, I suppose I'm still going to be able to do this part. There are a lot of limitations that I discussed. There are a lot of opportunities, knowledge-infused learning and explain AI, and there are a lot of applications that become possible. Manas, I think that should be my last slide.
Yeah. Yeah.
Okay.
Thank you, Doctor. So adding to what question that Vinita just asked, let me just motivate the audience with the idea of why I was so fascinated to go after like the knowledge infused learning as a bigger concept. And it comes down to a very old paper by Dr. Leslie Valiant in 2000, and also before that as well, which gives us interesting. The derivation is there in the paper. For the sake of time, I didn't put that explained, or like I didn't put it over here. But the bottom line of this approach was to describe this probably approximately correct learning concept, which is known as the PAC learning. So the idea of this PAC learning was that when we are trying to train a data, and we are doing a testing, the training error we want to minimize it to be 0, and for the testing error we try to kind of do some kind of a thresholding to attain a certain level of satisfiability over the training, over the modeling process. But and actually this entire training and testing trade-off actually relies on the number of hypotheses that your model is building. You can take any simple case of an SVM, support a vector machine, and it also depends upon the number. It also depends upon your epsilon as well, which is your thresholding, and also depends on the number of training samples that you have. So this multiplication factor is pretty huge in terms of the number of samples that you require and the number of threshold and number of hypothesis plane that you create. And you try to reduce the search space further by bringing an annotated data set, which has in itself has some threshold concept, which is, let's say we take it delta, delta. So this annotation concept that we bring in also further reduce the search plane. So you are trying to minimize your search space by saying by using this kind of like heuristic measures. So the idea of knowledge infused learning is we do not want to do a thresholding heuristically or without any background knowledge. Rather, we want to do the training and learning of the model and define its search space based on some expert defined knowledge or the knowledge that actually define the real world. So that actually forms a concept for the knowledge infused learning. And the interesting opportunity that you receive based on this PAC learning concept is a confidence and complexity, and also attainment of a robust classifier, which is also more or less a consistent classifier as well. So confidence is basically that you want more certainty in your model, which requires more number of samples. So this algorithm shows that if when you want more certainty in your data, you need more number of samples. And in terms of complexity, when you have a more complicated hypothesis, in order to prove that hypothesis, you need more number of samples. So idea is that for the knowledge infused learning is to gather the confidence and minimize the complexity. Whereas in that case, you are actually want to have less complicated hypothesis, and which results in the reduction of the data samples, and you need less number of data samples, and you need more complexity. So it's a pretty interesting trade-off between confidence and complexity, which actually drives the concept for the knowledge infusion. Let's take a very simple example that you have a true data distribution and the hypothesis data distribution, which in the recent conversations in conference where in a AAA it was talked about like a tacit knowledge. Let's consider that terminology. We have a tacit knowledge and we have a true data distribution. In existing data machine learning models that we try to know, we do already know we have our data and we have a label 0 and 1, and we want to learn this tacit knowledge distribution, and we want to minimize some kind of a loss function. The challenge occurs when these labels are not 0 and 1, but rather some concept classes, which are defined by some domain experts. Let's say if you have a image in a data set and you have an image and you want to have, you have that label of an image, which defines a real world concept. In such a scenario, it is very difficult for a model to label that until it has some information. Yes, definitely you need more, you can have more number of data samples to do that. But how about the idea here is, how about we do it with less number of data samples? So we try to define an infusion, which kind of is, you can consider that is kind of a mapping function, where you map your input data with the concept class using the knowledge and transform this entire mapping of dx and cx into the old traditional old-fashioned machine learning structure, which is basically you have the input distribution and the outcome is 0 and 1. So you are saying that whether the sample belongs to this concept class or not. So rather than labeling the concept class, you're actually saying that I'm just trying to say that whether this concept class occur or not. And if you say yes, then you can trace back and find which concept class does it belong to. So as a result, you are gaining better performance, and you're actually having a less number of samples to your for your training. So in order to do this process, there's a whole bunch of literature that has been created. For example, there's an event ontology, which actually describes your event. There's a very large literature on event extraction in social media and healthcare, as well as in in autonomous driving. And there are many other safety critical applications where event extraction is a main process. Rather than leveraging the data or a tweet or Twitter data or any social media platform or news articles, you can actually leverage an event ontology. It has a concepts and it has some other attributes as well. So you're using this ontology to bootstrap your machine learning structure by not letting it identify the patterns by itself, but governing its pattern recognition through an ontological structure. There's a recent famous interesting work that right now it is in progress, which is on the common sense reasoning graph by Alan AI. So it talks about that if you have a concept, let's say A related to B, there are many different versions of A relations and B that you can say there is a conjunction and there is a disjunctions and there is there's syllogisms and all those stuffs. Those things comes up and it gives a machine learning model a power to do reasoning. And that's where that graph on the top right shows that X repels, Y is attacked, but there are different ways of representing it. So those representations do not come naturally in DL. It can come, but you need more number of samples. How about you do not require those number of samples and you bootstrap it by using a knowledge graph? So those are the basic foundations of why we want to actually have a knowledge infused learning structure in place for explainability. So there are some challenges that Dr. Sheth just talked about in the previous. I just wanted to more go into the technical side of it, which says that when we the challenges that myself have actually looked at it from the social good application and the safety critical applications, like how do you ensure the consistency of labeling, especially when the label is not binary? For example, you have 4 labels in that data set. I have 5 labels in the same data set. How does the model behave in those scenarios? Do labels represent adequate semantics? For example, you say I have a label which is low, medium, moderate, and high, whereas I have a label which is more realistic and more clean, relevant to a human end user. So does that affect the model performance? And does that do we have the adequate domain knowledge to understand this data set? So maybe there are cases where you do not have sufficient knowledge and you have to completely rely on the deep learning structure. That's possible. In that case, you cannot you need more number of annotated samples. So that's something that also a kind of a thing that you need to work if we do not have a large number of domain knowledge. And then you also have that that when you're putting the model into use, how does the model behave in the consistency perspective? Is it consistent with the number of labels? It's just a repeat of the first problem, but saying that suppose you have 4 labels and I have 5 labels, how does the model behave in terms of consistency? So in all this answers, you can actually look into a structure where if you have a knowledge graph, or if you have an ontology or lexicon or dictionary, any source of information which is rich in kind of like a concepts, and you know the occurrences of those concepts occurs in your data set, you can actually utilize those to understand your data set much better. You are actually incorporating those concepts into your data set to actually enhance it in a way that your patterns make sense now, rather than meddling with the variations which occurs in social media heavily. So the knowledge-infused learning concept as large is actually distributed into 3 broader categories. Shallow infusion is where you are trying to improve your data. At the input side, semi-deep is about improving your model behavior, not touching your input data, but you know that this information is very much relevant to the data, but I would like to judicially incorporate it into the data and while the model is learning. And the deep infusion is that when I have different forms of knowledge, right, and I know that deep learning or any deep learning model learns abstraction as you go down the deep learning layers. You want to see that abstractions is also can also be supported by the abstractions in the real world. So those kind of like mapping of the layers again and again, which is not there in a semi-deep. I will actually try to explain that in the few subsequent slides. But the semi-deep is like, you know, a static knowledge, you don't change it. Whereas a deep infusion goes into a bigger strategy where you want to go with the abstraction in the knowledge, in the real world knowledge, and you follow that abstractions with the deep learning abstractions and try to see that if there is an information loss and what type of information, what type of information and what quantity of information can be added to that deep learning structure. So this comes down to the let me just give a very high structural view of shallow infusion. So shallow infusion is about like you have a self-aware or external knowledge, you enrich the data, and that data set goes into the deep learning, and you have a tacit knowledge which is a learned knowledge. And you what you're trying to do is you're doing a similarity testing, a very similar. If you have read the AlphaFold paper, or if you have read the AlphaGo paper, you might see that they have done a similarity based verification at the very end. So this happens when you have a kind of a knowledge infusion goes into the picture, or going into the deep learning, into your learning framework. Something in a semi-deep infusion, as I said, it is not about meddling with the data set, rather it is meddling with the model. So what you're trying to, in a very simple says, an intuitive scenario would be an attention. I would rather be more careful in my attention mechanism, rather than moving from probabilistic to more specific to explainability. I would rather be taking the attention mechanism to be a factor dependent on a weight matrix, which is W, which is learned by the mapping between the external knowledge and the representation that the model is learned. So you want Li is the latent representation that the model is learning, and you can say E is basically the knowledge that is coming from the external, and you want to learn a weight matrix which will govern my attention mechanism in my deep learning structure. And something very similar happens in the deep infusion, where you have different levels of knowledge and you want to add it to your layers as your model is progress. So this happens when there is a abstraction that happens in multiple layers of the deep learning structure, and you want that stratified knowledge to be appended to the layer again and again. So that kind of structure is in the deep infusion. Just to because we have a demo and all to illustrate this, I just wanted to I would just give a bigger picture of the deep infusion, but do not go that much detail into its applications. So in the shallow infusion part, I gave you an architecture. Now let's go into a little bit details of the methods part of it. So when you have data and you have a knowledge representation, when I say knowledge representation, consider to be a knowledge of ontologies, lexicons, as I said, those names. And what you're trying to do is you're doing an arithmetic mixing and or a non-linear mixing. So arithmetic mixing is a very common methods are dimensional reduction, PSC, PCA, or TSNE, or any of those methods which try to mix these different representations. And the second method that is another, which is a non-linear one, which is using the neural network, or an example in a very simple case that's recently used are multi-layer perceptrons. And what you get is a multiplexed representations. So when I say multiplex representation, the meaning is that these representations are mixed with each other. Your dimensions are pretty much, I think, yeah, if you do a concatenation, it will be increased, but in terms of a non-linear mixing, it will be still the same. So, but the concept is that you are bringing those different representations together, so that in certain case the information might not be complete in the data, but it is completed by the augmentation of the knowledge concepts. For example, let's take an example of like autonomous driving. I know that that in a school there is a speed breaker and there is a pedestrian way, right? And I know that there's answer that there can be a ball on the street coming from the ground, and there's another scene where there is no ball. But using that ball scenario, I can actually add that ball concept to the new one to actually see that there's a possibility of a ball coming into that scenario. So you are trying to add that kind of a shallow infusion structure in order to your model to work irrespective of in which domain or which region or which environment the model this autonomous driving structure is put to use. And there are many other downstream applications for NLP and NLU. On the bottom right, there are a bunch of like different methods which have been developed along this line of shallow infusion, and they are basically trying to say that you are actually capturing knowledge in terms of by using word level features or character level features or using attention level mechanisms in improving your input data structures. There are other methods that I would actually bring this to the audience who are from like the interdisciplinary phase. There are a lot of words and phrases that people have talked about in the other domains. For example, psycholinguistics, cognitive theories are there, and they are behave like, for example, in a COVID-19 there's a very fascinating study. I don't remember, but there's a very fascinating studies on activities of daily living. And you know that their activities of daily living are affected because of COVID-19, and you want to you want to assess the psychological impact of COVID-19 on in some social media sphere. That kind of a knowledge of activities of daily living can be brought in for making a more explainable outcomes. So very similar, like there's a nouns and pronouns and verbs describe the human behavior. There are sentiments and emotions where you rather than going from -1 to 1, you're extending it to from -4 to 4 with richer categories and subcategories of sentiments and emotions. And another concept which is very much common in natural language processing is a semantic role labeling. So rather than having Mary sold the book to John, I would just replace the sentence with agent, predicate, theme, and recipient concept. And the ordering of this will help me find the patterns. So that kind of abstraction, if given to at the initial stage of the deep learning or machine learning structure, would actually help in a better outcome, because now you know what, because that actually it will limit your variations in your data set. So that's the whole idea for knowledge infusion. So minimizing the variations and gathering more explainable and effective patterns that can be identified. So let's take an example right now about some very
Manas?
similar in the COVID. Yes.
Just a minute, just a time check, because we just have half an hour left and we have 2 more
Sure.
sections.
Yep. I'm just wrapping up.
Yeah.
So now consider this example of flu pneumonia that happened in COVID-19. And the question is it true? So you have a true 0.64 and a false of 0.36. That comes when you are using an attention matrix. This is what we saw in our COVID data set. And what we are trying to say is that if we have, it's the same question, but if we have using a knowledge graph in structure and replace this entire tweet with affected population communicable diseases, and then we say the answer true, it comes out to be more true and less of false. So you are gaining more confidence in your data set with this structure. And the intuitive method that we have used are very much similar to the Jaccard similarity and cosine similarity to abstract the content from tweet to this level of concepts. A very simple example that was talked about was the knowledge graph computing the scene similarity in the autonomous driving scenario as well. Another one is the semi-deep infusion, where we are actually more focusing on the learning and inference and regularization. So so this is something that we are working on right now. So initially what I have found is learning and inference and regularization to be the two main methods of semi-deep infusion, but there can be many more.
Hello, is Manas dropped?
Looks to me like he did. I
You
don't know
can
what
take over. Kevin, you can take over.
I can take over then in that case. Hello.
Yes.
Yeah,
Sure.
go ahead.
Sure, let me share my screen and yeah. Yeah, so I think, can you guys see my screen?
Yeah,
Yes.
we can.
Right. So maybe, what we can do, we can, like Manas has already, presented.
Let us just do, in the interest of time, something a bit rapidly. Go up. 60, the graph, let's go to that graph. Not that, go up, not one above there, still ago. Yeah, slide 55.
Yep.
Or 54, yeah, just keep it there. Let me give a couple of things and then we can move on.
Sure.
So, and can you go one back? He has not done it, right? We're not done this.
This is not done yet. Yeah.
Okay, and one more back. Very quickly, I'll do something. All right. So what is happening here is that you see on the at the top you see the text, and the words that are in the text are associated with the concepts in the knowledge graph. And with that, now the learning system has more to work with, not just what is the word and the statistics associated with the words, but actually all the power of all the representation that is there in the knowledge graph. That is captured in this matrix that you see here. There's a DSM-5 knowledge graph, and then there is this DSM-5 post correlation metrics, which then gets embedded into or integrated into the deep learning algorithm. So what happens is that if you were to decipher what is in the learning algorithm, you can go back to, you know what, I not only got that word, but I got larger context associated with that word. That word is about drinking. That word is about obsessive compulsive personality disorder rather than just some word. And this is what experts or humans would be thinking about when they, because humans are actually interpreting the words and associating them constantly. This is called trailblazing in old 1945 article by Vannevar Bush. Next.
Yep.
Again, in interest of time, I'm going to pass that. But in here, what you're seeing is that on the left-hand side is what you'll be using, for your deep learning. On the right-hand side, in the orange, is the additional knowledge that came from DSM-5 and DAO is drug abuse ontology. So now inside, what you have is not just the statistics from what correlation and all the patterns you can get, but you also have additional knowledge coming from knowledge graph. This is what makes your deep learning algorithm a lot more smarter, a lot more aware of what's happening. Next. So here the graph shows a whole variety of choices you have. In the left hand side, you start with lexical and statistical features, and you can see there is performance still not good at all, with 30% error rate. Then you have lexical TF-IDF feature, nothing so much. Then you have contextual feature. Now you got significant improvement. Another huge improvement comes when you put in DSM-5 knowledge hierarchy, and now you get 0.04. Further, you have DSM-5 plus additional knowledge of drug abuse ontology, and then you are incorporating slang terms and other things. And you can see as you incorporate more and more knowledge, so this is the improvement of performance that we were talking about, right? The quality of results. Yep. But it also comes with the explainability. Okay, next. We can pass this in the interest of time.
Yeah. Yeah, so I think we can jump on to the next section, Dr. Shet.
Okay, yeah, let's do that.
So these are a bunch of good resources, by the way. You guys can refer to the deck afterwards as well. But I think we, in the interest of time, let's move the next topic, which is explainability and interpretability using domain knowledge, right? So what we have seen with first section where Dr. Seth implied that the impact of semantics when it comes from the symbolic knowledge, right? It may not be captured that well in statistical learning, which generally happens via deep learning, right? So there is an opportunity to do knowledge infusion, right? Where domain knowledge can be infused to make it better. Similarly, another problem that deep learning system has is black boxness, right? We don't know what's going on underneath. So to make system explainable and interpretable, right? So that's also another area, and where domain knowledge can also be helpful, right? So ultimately, explainable systems using domain knowledge would be better to get easily adopted into different domains, as well as with more transparent decision making, right? So it could cater to more responsible AI or trustworthy AI. So let's go deep into the section. So there are some bunch of definitions, which it is like very intuitive way to define them. Explainability is ability to generate human comprehensible explanation around the decision making process. So and it is very natural to human that any decision that we take or we basically take it from someone else, right? We are keen to know why the decision, what's the explanation beneath. So same applies to deep learning model. We can't just rely on the predicted outcome. So we need explanation behind that, and that would need interpretability. And typically, like term explainability and interpretability, people do use interchangeably with ambiguous boundary, but there is a definitely a different meaning with both this term. Explainable system would need interpretable subsystem, right? So interpretability is about discerning the internal mechanisms of any module, right? So if you want to combine both of them, then explainability can be said as interpretability plus completeness. So let's say a system which is explainable has n number of subsystems. When each of those subsystems are interpretable and their orchestration between those subsystems is also interpretable, it would very easily give rise to an explainable system. However, an explainable system has to be interpretable, but reverse is not valid, because many a time what would happen, a system would be interpretable, but the explanation has to come in a human understandable form, right? So either with natural language or with visual depiction, so which human can easily understand it, a normal human, right? However, interpretable or the outcomes of interpretations can be statistical in nature, or it can be conceptual in nature, which would require some kind of an expertise to distill that or to understand that. So with this definition, let's move ahead. I mean, these are the goals of explainability. We all know that these are very important goal, and explainable system would need to cater that, and that would lead to easy domain adoption. Once again, I think we have a lesser time, so I'm not going into each and every goal which is mentioned here, but what we can say, let's say, just to give one example, like causality, right? So ability to invoke cause and effect relationship among features, that's like one of the very important goal that any system would have. Now, machine learning system would typically be, stochastic or probabilistic, and they would generally work on the correlations. They would not invoke cause and effect kind of a relationship. However, to do that, there is a need of domain knowledge or the knowledge graph, that we would have to basically, we need to verify with domain knowledge, and another, to infuse such relationship, we need to play, the domain knowledge infusion kind of a setting, right? So this is just an example, but with each of this goal, there is definitely, a role that knowledge graph plays to attain, different dimensions of explanations. Right. Now, yeah, this slide I like to spend some time on, so where are we, right? So we, in the journey of machine learning, we used to have like right from a rule-based system, expert system, to decision tree, to support vector machines, and nearest neighbor, and all those transparent model used to be there. Those transparent model, we were able to easily understand, because either they are so simple that we can simulate in our mind, or we can decompose that model or that system into different component, where each component can be understood in a human comprehensible manner. Or if it is bit complex, then we know exactly the procedure or algorithm, which is transparent enough, which basically gives us the set of instruction on how to transform input to output, outcome or the prediction, right? So there is a total algorithmic transparency. So all, like, mostly, those models which are termed as transparent model, like regression techniques or decision trees, SVM, they fall under these categories. However, with deep learning, there are like bunch of black box model. Let's say GPT-3, 175 billions of parameter. Like, I mean, there is no way we can understand like what's going on inside that. So for such black box model to understand what's going on in its different mechanism, we need post-hoc explainability. And then research community has been pretty active recently on this area. As a result of that, there are a bunch of techniques. I mean, we have just clustered 7 out of them, which we'll cover in the next few decks with examples, which basically go and discern or dissect the black box model to understand, like what features were important, or what rules were captured in the model, or what was the locality in which the decision has been taken by model, or how to visualize, the importance of various stages in for the decision making, right? Along with that, there is a bunch of other research which generates explanation, right? So either pre-generation of explanation, feeding into decision-making process, and then predict. So which we can say explain, then predict. Let's say, we want to make a prediction of multi-hop kind of a question answering. We want to predict an answer or a sentiment analysis, right? Then it's like, we are generating explanations where explanation can be thought of like a meaning of a word, right? Or a knowledge, or a symbolic knowledge, so that we feed into the model along with the actual input, and model would be able to do better because the explanation has also come along with the input. And then, in the explain then predict setup, the prediction would be better, and it would be aligned towards explanation, and that explanation can come from a domain knowledge, right? So to make prediction aligned to explanation would give not only the more accuracy, but also the transferability or generalizability in real world use case, and it would not be limited to just training data or the test data or dev data, right? So because those explanations are generated by taking domain knowledge into consideration, right? However, such system can still not be called explainable system, because both this process of generating explanation or augmenting explanation to input data and then making prediction are still black box, right? So if that is the case, then the system though take help of explanation, but it is not still an explainable system. Similarly, the other way around, where you predict first and then you explain, or a prediction can go along with the explanation. There is, recent model WT5, which basically not only generate the prediction on the NLP task, but the first token would be the prediction, followed by that there would be a natural language explanation to that, right? So such system has explanation inside that, but still the lack of interpretability would not allow them to be classified as the explainable system, right? So that's where this was an important aspect to know. So now these are the things that you guys can maybe, if interesting, can refer because it's a bunch of knowledge around like the different methods of explainability and what's the pros and the limitations and strength of each of them, right? So I'll just skip that. LIME is one of the pretty popular and effective method of explanation. We can see the example, right, where data was sneeze, weight, headache, no fatigue, age. These are the features, and the model is predicted whether it is a flu or not. So then yes, it is a flu. Then LIME, what LIME does, it searches the locality of that particular input instance, and in that locality, what are the features which are impacting the outcome. Then it turns out that sneeze and headache are like common features which are found in the locality where the prediction is flu, right? However, no fatigue is like is a negative evidence to that, right? So now such explanation would help anyone to understand what kind of flu it is, or how confident the decision of the model should be believed on, should be adhered to. So explanation by example, we just surface the similar examples which are similar in terms of prediction, or they are influencing the prediction process, right, or the decision of the model. Integrated gradient, this is like one of the another very popular and effective method to compute feature relevance, like what input features were responsible with what extent for the decision making, right? If you can see in the visual image, integrated gradient is the second column and the just gradient is third column. So just gradient we all understand, like any change in input, how much change it will make to outcome or the prediction outcome. So that's the gradient. Now gradient can be noisy because it could have reached plateau and it may not be doing it bit in the current locality or the neighborhood, but integrated from the reference till this point of time would give much better explanation. So we can see in camera and a school bus and those kind of example how the pixels were making meaningful feature attribution or feature relevance. Similar in the text domain, when we make prediction that it is numeric, we can directly say it is because of how many kind of keywords, right? So this is another method. Integrated Hessian is one order, on top of integrated gradient visualization. I'll skip all these things, and we can come to this, right? So this particular slide gives us, it merges two different fields, which is knowledge-infused learning and explainable AI, right? Because most of the method that or like almost all the method, they make decisions to come up with explanation or interpretability. Now those decisions, that's a line, it works in the locality. So now how should one consider a locality? That's a question domain knowledge should answer. Explanation by examples. How should one consider similar examples, right? So that's another question that domain knowledge should answer. Not, by just taking Euclidean distance or cosine similarity may not be the single case. Hey,
yeah, very sorry for the interruption. So it is just a time check.
Yes,
if
yes.
you can
So
wrap up in
just
the
a
next
minute
couple of
more,
minutes.
I'll conclude. Thanks for that. Yeah, right. So
Thank
basically, in this slide, for against each popular explanation method, we are seeing the opportunity to infuse the knowledge. An Embibe use case I can show where we are predicting students learning outcome, where the knowledge graph, academic knowledge graph and historical data lake in a shallow infusion manner and deep infusion manner, it can not only predict the score of the student but with the explanation which are academic in nature. Let's say projectile motion was the concept where user was weak, but what was the prerequisite concept which led to this kind of academic weakness, and as well as the behavioral outcome, right? And yeah, these are some slides I'm gonna keep. This one is important. Knowledge aware loss function can do wonders, right? So let's say concept K1 is prerequisite to concept K2. That's a domain knowledge. No deep learning model would know unless we feed this kind of a knowledge. And if we fit that into the loss function of the domain of knowledge tracing deep learning model using LSTM, it gives like really good accuracy improvement, as well as it is plausible from explanation point of view. Model simplification. Yeah, this is another explainable, like last use case I will just try to explain. A student moving from unlearned stage to learned stage, the probability is 31% without seeing a feedback. But when they see feedback, they move from unlearned to learned with 38% of probability, right? So there is a 7% of improvement. Now this is basically so motivating, not only to design the feedback page, but also what feedback page is more relevant to what cohort of the user, and we can do a lot more, right? So rather than just predict concept mastery, the transition is important. Yep. So with that, we have basically like quickly tried to cover that. If there is a minute more, then I think Ankit can quickly show a KG demo and we can have a question answering session.
Yeah, sure.
Yes, yes. Please
Yeah,
go ahead. Ankit.
sure. Okay, next. So what I'll be presenting is about the knowledge graph use case at Embibe. So at the Embibe knowledge graph, the backbone of the system at system of intelligence at Embibe is the knowledge graph. So now at the Embibe, we consider knowledge graph is made up of concepts, and the concepts are connected with directional relationships, and there are specific types of relationships which are academically important that we have considered. Now, on an average, we have till now 100,000 of the concepts. Relationships are in the range of 800,000, and competencies are approximately 125,000. Now, competencies are the very important, most granular piece of the knowledge assessment, where if you see the NEP as well, the government of India is also asking educations to be evaluated not only based on the concepts, but to go more granular and to test the students' competency on each of the things that they learn in the classroom. So this we have modeled, and at the backbone of the Embibe's data intelligence platform, knowledge graph is serving its purpose. And by leveraging this, we have came up with some solutions which are able to generate the students which are able to understand the students current standing on each concept at each competency level, and based on that we are able to predict the personalized path of learning to the students, such that
Okay,
his overall.
I'm stopping my screen share so that you can do that demo, right?
It is there in the slide. We can just play the video. Yeah.
Okay, sure, I'll do that.
Yeah. Yeah, so I'll continue. So over there, I was saying that to improve the learning outcomes of the student, we just go to the next slide. Next, next, next. Yeah, this one. Just play it. I'll just narrate this. This is very important to understand. This is for Indian curriculum CBSE. These are all the dots which represents the concepts. Now, if you see that there are specific types of relationships, I have enabled the relationships, and for a specific subset of the knowledge graph, we have 127,000 relationships encompassing across 30,000 concepts. Now, if you see that if I color the nodes with different selection like subjects or exams or different grades, then you can see that how they are interconnected. Now, by using this as a backbone of the system, you can easily eliminate the you can easily implement the gradeless learning, and you can experience your student with the gradeless and platform of education. Now you can see here that these concepts are so connected, and they also represent the academic sequence of the which is very difficult to model for an educational platform, because that's where you are able to derive that which particular sequence in which the concept should be studied, such that you maximize your learning outcomes. Now here the colors represents the mastery on the given concept, and little triangle represents the competencies attached to that concept. And you can see that the different grades concepts are interlinked. So if you know the prerequisites from the previous grade, you can easily ask the students the questions from the concepts which are prerequisite to the current concept if the student is not performing well enough, and you can mitigate the deficiencies in the learning. So the academic sequence and the prerequisites are very important relationships that Keyur also mentioned, that when we model the loss function using those domain knowledge, we can easily interpret the models, and that is proven by the platform and application at Embibe, where we are able to see the improvements in the learning outcome by understanding how the learning outcomes are improving. Yeah, so I think in interest of time, I'll stop here, but if any questions, we'll be happy to answer.
Uh, Thank you, all the tutorial speakers, and actually, I feel very bad to cut it short. To borrow your own words, this tutorial was like very explainable. It was exhaustive, and the concepts were like explained in so simple and interpretable way, and also in a complete manner. It was really interesting listening to you all. So we had actually some questions, and those are answered already by the tutorial speakers. So I believe the attendees, they have their answers. And for any more questions, you can reach out to the speakers offline. There is, however, one open question that asked by Jayati Deshmukh. She has asked, the demo is very interesting. Is it available online? So, Ankit, would you like to comment on that?
So that particular demo is behind the VPN, but this slide is already shared where it is having the video of that.
Okay, okay. Thank you. So I guess that addressed the question. So I thank all the speakers again um, for a very nice and wonderful session. So thank you.
Yeah, thank you, everyone. Thanks, panel, for hosting us, and thanks to all the attendees for kindly, listening us.
So thank you. I think it was a very involved tutorial and quite relevant. That the explainability part of AI is, I believe, is a very relevant thing these days. And special thank to Professor Amit and for joining in at an odd hour to be kind enough to give this tutorial. And thank you very much. Thank you.
Bye.
Bye bye.
Bye.